Hello students, in the previous lecture we had discussed the definition of groupoid, semigroup, monoid group, abelian group and non-abelian group or non-commutative group. Now in this lecture we'll illustrate by taking definite or indefinite sets to show that the algebraic systems form a groupoid, semigroup and monoid, and in the next lecture we'll discuss group, abelian group, commutative group formed by finite or infinite algebraic system. Now to understand the definition of semigroup, monoid will be discussed in this lecture. So for that let us take first example to show that the set of natural numbers form a semigroup under the composition of addition. Answer to this is given is natural number set, composition addition. So algebraic structure will be natural number with population of addition, random addition. So natural number is given to you. So if I compare it with the definition of semigroup have a this algebraic structure, natural number and positive binary of addition. Non-empty set is natural number and binary composition is addition. So we'll show that this algebraic structure form a semigroup. When it form a semigroup, a closure property and associative property holds true in the set of natural numbers. So first we'll prove that we'll show the closure property. Since a plus b belongs to n, for all a belongs to n, that is, if out of infinite number of natural numbers, if you take two natural numbers a and b, their sum is also a natural number, implies closure property to hold true in set of natural numbers. Means next is associative property. Since a plus within bracket b plus c is equal to within bracket a plus b plus c, for all a b c belongs to a set of natural numbers. Now if out of infinite number of natural numbers, if you take any three natural numbers, then if we add second and third number, then the resultant of that will be added to first number, and on the other side if you add first and second number, then we will add the third number to that. Both left hand side and right hand side give us the same natural number. So natural means this implies associative property holds in the set of natural numbers under the binary composition of addition. Now the set of natural numbers with the binary composition of addition, binary addition form a semigroup because both the property closure and associative property hold true in set of natural numbers. Now let's discuss another example for that. Show that the set G of matrices of the type whose first element of the first row are same, and first column are same and first and second column are same, and both are real numbers and they are such that the sum is not equal to 0. This type of matrices form a semi-group under the operation of multiplication matrices, but it will not form a monoid. So in order to show that this set G form a semigroup, you have to show that closure property holds in G and associative property holds in G. For that we have we consider set G we consider set G we have to show that closure restricted property holds true in the set of this in the set of integers in the set of in this algebra holds true in this algebraic structure, but the identity element does not exist. Suppose property that A and B belongs to G. If A and B belongs to G, the first element of A and first element of first row are same, element of second row are same, and their sum for sum of these elements is not equal to 0. Similarly, B first two elements column element same, second column same, and sum of these element is equal, not equal to 0. B2 elements, B2 elements 1 into now x1 plus y1 is not 0 and x2 plus y2 is not 0. They are two non-zero numbers. Their product will not be equal to 0. This is true in mathematics. Now let's multiply A and B. Go to column multiplication. So we got a resultant matrix this. Now this product will belong to G if the sum of this element first to first column and first to second column is equal to 0. So first implies that this is not equal to 0. First result this and multiplied x1 by 1 plus x2 by 2. The result is same as the element of this sum plus this is multiple. Show that product belongs to G implies G is closed under binary calculation of multiplication. Next is associative property. Since matrix multiplication is always associative, that is for all ABC belongs to G, A into B into C is equal to AB into C. This is true. This is true. We have proved it in the earlier class. We have proved it in the class, so this will be applicable to all the examples. Therefore, this implies associative property for G and G with the binary composition of multiplication matrices form a same. Now, in order to show this will not form a monoid, we have to show that identity element does not exist. So let us go that this E is the identity element of G. Means E is of type A first element of first column same, element of second column, and the sum of this A and B is A plus B is equal to not equal to 0. If this is we show this is identity element. If this is identity element G for all A belongs to G, such that x plus y is not equal to 0, A into E is equal to A is equal to E into A. And we substitute the value of E and E in this equation, we got and multiplied them, we got these matrices of this matrix of 2 by 2, this matrix 2 by these three matrices equal. If we take first set of two matrices, they are equal, they are same type, and the corresponding element same. When we compared the corresponding events, we got A is equal to x upon x plus y, B is equal to y upon x plus y. Similarly, when we compared the second and third matrix, we got x into A plus B is equal to x, y into A plus B is equal to y. That is x into A plus B minus 1 to 0 and y into A plus B minus 1 to 0. When we added equation C and D, we got x plus y into this is common from both the numbers. So A plus B minus 1 to 0. But x plus y not equal to 0. Now for this equation to hold true, A plus B minus 1 must be equal to 0. So A plus B equal to minus 1. Now we can't we don't have a single ordered pair AB value of AB such that their sum is equal to 0. So if A and B are not unique, A and B are not unique implies E is not unique. E is not unique implies thus the elements of E is not unique. Thus element G is not unique. Elements of G are not unique. Elements of G are not unique. Hence identity element in G does not exist. Therefore, G with binary composition multiplication matrices does not form a monoid. It forms a same group, but does not form a. Let's discuss another example of sets. Let X be any non-empty set. Let Px denote the power of the set X, then show that Px form a monoid under the operation of intersection of sets, and Px form a monoid under the operation of union of sets. So first part will show that Px form a monoid under the operation of intersection of sets. So Px is a algebraic system, and binary property is intersection. So we'll show that. I mean, we have to show three properties: closure, associative, and existence of identity element. So closure property for all AB belongs to Px, two sets A and B belongs to Px. There are two implies both are subsets of X. Yes, if they belong to subsets of X, because Px is a set of all the subsets of X, all the possible subsets of X. They are subset, therefore their intersection is also subset of X. Implies A intersection B also belongs to Px. Implies, this again implies, hence that goes back to Px. Associative property. Since the associative law holds under the intersection of sets, therefore in particular it holds in Px. That is, for all ABC belongs to Px, A intersection with B intersection C is equal to AB intersection with C. A intersection B with intersection C means if you take three subsets of any three subsets of Px, if we find this second and third, and then with intersection with first, if we find this first and second, and then then the resultant set will be intersected with the sets, third set, the elements of both the sets comes out the same. Implies the associative property holds in the intersection of sets. Now, existence of identity element in Px. Now, for all A belongs to Px, there exists X belongs to Px such that A intersection with X is equal to A is equal to A intersection with X. If you take any set of Px and X also belongs to Px, X intersection A is A, and A intersection with X is again A, implies X is the identity element of Px. Hence, the algebraic system Px with binary intersection form a monoid. We can discuss this property as well as the union is monoid with help of this example. X which is this and power of set is this. We'll discuss it, and these both examples will become very clear to you if you apply these. X will be for this finite set, like this, then for the finite set. Now next is for the union of two sets is forming monoid. For union of union of power of sets forming monoid. For that, for all AB belongs to Px, both are subset of Px. Therefore, their union is also a subset of Px. That is, A union B Px implies Rose-Berkeley holds in. Next is so union of two sets. Rose-Berkeley holds for the union of two sets of the Px. Now, next is associative property. Since associative law holds under the union of sets, in particular, it holds in Px also. That is, for all ABC belongs to Px, A union C is equal to A union B union C. That is, if you take any three sets of out of Px, if you find union second and third, then the first and second and third, both the sets will be same. Implies associative law holds for the union of sets in the algebraic system Px. Now, it can determine the existence of the identity element in Px. For all A belongs to Px, there exists phi belongs to set belongs to Px, such that A union with phi is equal to A is equal to phi A. Phi is an identity element of Px under the binary composition of union of sets. Hence, identity element exists implies this algebraic structure form a Alright, next example. Next we will discuss the functions. Let Mx be the set of all mappings of a monotony set X into itself. Then show that Mx form a monoid under the operation of composition of functions. So solution for this is given is Mx is a set of all functions such that f is a function from M to x, right? Now our aim is to show that the algebraic structure this consisting of algebraic system Mx and composition of functions this form a first property. Let f and g belongs to Mx, two set functions. Then their composition f of g such that f of g, the function from x to x, is also mapping. That is f of g belongs to Mx for all f g belongs to Mx. If you take any two elements of Mx, their composition also belongs to Mx. Implies property holds for the composition functions. Associative property. We have taken three elements belongs to Mx such that small x belongs to x, element of the set x. Then composition f with the composition of f of g of h of x, f of g of h of x is equal to f of g of h of x first. Similarly, f of g of h of x is equal to f of g of hx is equal to f of g of h of x. First and second implies that f of g of h is equal to f of g of h. F of g of h is equal to f of g of h for all f g h belongs to x. Associative law holds in the set of elements. Existence of identity element. Now, for all f belongs to Mx, there exists an identity mapping I from x to x such that defined by I of x equal to x for all x belongs to x such that f of I of x is equal to f of ix is equal to fx. I of fx is equal to I of f of x is equal to fx. First and second implies that f of I is equal to I of x for all f this. I is an identity mapping of f mx. Therefore, the algebraic structure mx with binary composition of this form. Now, let us discuss another example. Let M2I be the set of all 2 by 2 matrices over the set of integers. In the set of integers, show that the set M2I form a monoid under the composition of multiplication of matrices. Given is M2I, set of all matrices such that all the 4 elements of 2 by 2 matrix are distinct and all are integers. This property, if we take 2 elements belongs to M2I, means both the matrices A and B are just of the second order, and there all the elements, all the 4 elements of A and all the 4 elements of B are different, and all the eight elements are integers. When we find we will find the product. After find the product, elements of the resultant matrix are this integer, this integer, this integer, integer into integer, integer, integer into integer plus integer, and this again a integer. Similarly, this integer, integer, integer. So now product is a 2 by 2 matrix, and all the elements of this are integer. Therefore, product belongs to M2I. Implies closure property hold in M2I. Associative property. Since the matrix is associative, in particular, associative law holds in M2I. That is, if you take any 3 matrices belong to M3, M2I, then if you take second and third matrix, then multiply first. If you first second matrix, then with third, both the matrices comes out to be same. implies associative law holds in M2I. Third is existence of identity element. For all A belongs to M2I, there exists I of the type is diagonal element 1 1, nodal 0 0, or second order matrix. Second order matrix, of the M2I belongs to MTI, so that A into I is equal to A into I into A. I is the identity element of M2I under multiplication. Hence, M2I form a monoid. So above discussed examples are general infinite algebraic systems. Now, in the next lecture, we will study the concept of group, abelian group, and non-abelian group. Group for the finite as well as infinite algebraic structures. Thank you.